স্বর্ণলিপা, তুমি এখন হোস্ট, ঠিক আছে?
হ্যাঁ স্যার, হ্যাঁ হ্যাঁ ঠিক আছে, থ্যাংক ইউ। Well, so let's start. Um, I will be solving problems from quiz 1, and I have come to know that problems 2 and 5, these two are unsolved in the tutorials. So let me first solve problem number 2. So it says that the Lucas sequence, the sequence is given 1, 3, 4, 7, and so on, and it is defined by a1 equals 1, a2 equals 3, an equals an minus 1 plus an minus 2. And we are supposed to give a closed form expression for an. Also, we need to prove that an is equal to order of 1.75 to the power n. So we will solve this problem using generating functions. So let us consider the generating function f defined by fx equal to sum over ai x to the power I from 1 to infinity, where ai is the ith Lucas number. Okay, so fx equals sum of sum over I from 1 to infinity ai x to the power I. This can be written as x plus 3x square plus ai x to the power I from 3 to infinity, because we know that ai a1 is equal to 1 and a2 is equal to 3. Now this equals x plus 3x square plus sum over I from 3 to infinity ai minus 1 plus ai minus 2 x to the power I, as because we know that ai is equal to ai minus 1 plus ai minus 2 for all I greater than equal to 3. This is equal to x plus 3x square plus ai minus 1 x to the power I plus, this is from and this equals x plus 3x square plus x I from 3 to infinity ai minus 1 x to the power I plus x square I from 3 to infinity ai minus 2 x to the power I minus 2. So This can be again written as this. So if you just perform quite a few calculations, you can check that this is equal to x plus x square plus x fx plus x square fx. So this is pretty simple. I mean, you can just check it. So fx is equal to minus x plus 2 plus 2x square by 1 minus x square. Let alpha and beta are the roots of the denominator 1 minus x square. In that case, let's write fx as this. Now, it is easy to say that 1 minus x square has roots minus 1 minus root 5 by 2 and minus 1 plus root 5 by 2. And again, solving all these things, we have a equal to 1 and b equal to 1. So now fx can be written as well, so we can check from here that alpha beta is equal to minus 1. And using that, we have this thing. Now this is equal to x into 1 by alpha beta x plus 1 plus 1 by beta alpha x plus 1. This is again equal to x into 1 plus beta x inverse by alpha plus 1 plus alpha x inverse by beta, that is again equal to x 1 minus beta x plus beta x square, simple binomial expansion, minus beta x cube plus so on by alpha plus 1 minus alpha x plus alpha x square minus alpha x cube plus so on by beta. Now this equals x into 1 by alpha plus 1 by beta minus beta by alpha plus alpha by beta x plus beta square by alpha plus alpha square by beta x square minus beta cube by alpha plus alpha cube by beta x cube and so on. This equals 1 by alpha plus 1 by beta x minus beta by alpha plus alpha by beta x square plus beta square by alpha plus alpha square by beta x cube minus beta cube by alpha plus alpha cube by beta x to the power 4 and so on. Therefore, fx can be written as this thing. Okay, this thing. So now we have a equal to minus beta to the power n minus 1 by alpha plus minus alpha to the power n minus 1 by beta for all n belongs to the natural numbers, the set of natural numbers. This equals minus beta to the power n minus 1 beta plus minus alpha to the power n minus 1 alpha by alpha beta. This again equals minus 1 to the power n alpha to the power n plus beta to the power n, which means minus alpha to the power n plus minus beta to the power n, and that is 1 plus root 5 by 2 whole to the power n plus 1 minus root 5 by 2 whole to the power n. So we have obtained the closed form. Now we also need to show that an is equal to order of 1.75 to the power n. To do this, we will use strong induction. So to do this, we need to show that an is less than equal to c 1.75 to the power n for some constant c greater than 0. So let's do this. So here for n equal to 1, we have a1 equal to 1, and that is obviously less than equal to c into 1.75 for some c greater than equal to 1. So our basic step is done. Now for the induction step, let ak is less than equal to 1.75, c into 1.75 for some c greater than 0. And for all k less than equal to n minus 1. Then an equals an minus 1 plus an minus 2, that is less than equal to c into 1.75 to the power n minus 1 plus c into 1.75 to the power n minus 2 by induction. And this is equal to c into 1.75 to the power n minus 2 into 1 plus 1.75. So we have c into 1.75 to the power n minus 2 into 2.75, which is clearly less than equal to.
Hello, ma'am.
Yeah.
In induction step প্রথমে a k less or equals to c into 1.75 whole to the power k হবে মনে হয়।
Sorry,
a k less or equals to c into 1.75 whole to the power k.
no, it won't be k because a n minus 1. Oh, sorry. Okay. Sorry. Thank you for pointing it out. I forgot to write that. Sorry. I'm really sorry. So so this is less than equal to c into 1.75 to the power n minus 2 into 1.75 square. Now this thing is easy to check, and this is clearly equal to c into 1.75 to the power n. So do you have any doubts here up till now? Please say yes or no, otherwise I will not be able to.
It's okay.
No, ma'am.
Okay.
Ma'am, it's okay.
Okay. Now I will solve problem number 5. So So it says that suppose we are given a graph G, simple connected graph, and the set of vertices is denoted by V and the set of edges is denoted by E. Also, we are considering S to be the set of all spanning trees of G. I think you all know what a spanning tree is.
Yes, ma'am, it was covered in the script, ma'am.
Okay.
Also,
So
I just let others tell once. I think problem 5 was covered in first tutorial, if I am not
oh,
wrong.
but I was being told that it was not covered.
I am not completely sure, so others who are there can tell. I do not exactly remember, but I think we did 5, 6, and 7 in the first tutorial.
Oh,
No, actually, there was a problem in problem number 5, actually. So the graph was simple connected, but
Hmm.
Sir has given an example, assuming that it is not connected, actually.
Oh, okay. So yeah. He asked me to correct it. This thing is actually true. I mean, there won't be any counter example. So that's why he told me to just solve it in the class. Okay.
Now, if I give a counter example, this is right.
Sorry.
Is there any proper proof this for the problem 5?
Proper proof in the sense, yeah, I mean to say, I can give you an idea. Okay. So I think that will help. That will help.
Our deadline for submission is over as it is, so I think we can proceed with a complete proof today.
Okay.
So
So
we have
actually,
already submitted the assignment.
yeah.
Well
You
first
people have
dated,
already
right?
submitted the assignment. Yeah.
Yes.
Okay.
Ma'am, I solved this actually proved the by actually for the using real analysis actually. I take the set is a collection of polyspinning tree of G, and I define a metric function on the set S, and then the actually I want to see here the is does not satisfy the all metric space property.
Okay. I'm actually not getting what exactly you were saying, but so are you talking about problem number 5?
Yes, ma'am. Yes.
Okay, so you have written this solution. I mean, whatever you were saying, you have written this solution in the quiz.
Yes, ma'am.
Okay, okay. Just I think you will have to talk to sir about it. Okay, so you can tell me the solution just for now. Maybe I will think it later on. Okay. Hello.
Yes, ma'am. Yes.
Okay. Please let me know your solution.
Actually, ma'am, I consider actually S is the set of all spinning tree. Okay.
Hmm.
I define a metric property. Actually, I define a function on the set S.
On the
And
set
D-
S. On the set
Yes,
S.
yes.
Okay.
Yes. And suppose D is
Sorry, your voice
Your
is
voice is
breaking.
breaking.
the set S and
Hello. Your voice is breaking.
Suppose TJ is the spinning tree of. Okay, ma'am. Okay.
Hello. Hello.
Yes, ma'am.
Yeah. Your voice was breaking. Can you please repeat?
Yes, ma'am. Actually, I define a function on the set S. Suppose
Yeah.
Ti and Tj is the spinning tree of G, and Ti Tj is the element of the set S. Okay.
Hmm.
And D is a function on the set S. D Ti Tj equal to the number. Actually, we define the function such that D Ti Tj equal to the number of actually H is difference. Actually, I mean the H in Ti, but this H is other actually those H in Ti, and this H is not in the Tj. Okay, and my problem is the Ti Tj when the actually I forget the problem. Okay, just let me see.
Okay. So the problem is, okay, let me first tell you the problem. So the problem is, we are given a simple connected graph G. V is the set of vertices, E is the set of edges. We also have S to be the set of all spanning trees of G. Now, we say that the spanning trees T and T prime are neighbors if and only if T contains exactly one edge, which is not in T prime, and T prime contains exactly one edge, which is not in T. So now, we are now constructing a simple graph using these spanning trees. Let us denote this graph by G prime. G prime has a vertex for each spanning tree in S, and each of the two vertices in G prime, they are adjacent if the corresponding spanning trees are neighbors of each other. And we need to show that whether G is connected. Yeah, now, is it Dhananjay? Hello?
Yes, ma'am.
Yeah. Then now please let me know your
And
solution.
they are actually neighbor to each other when dTij equal to 1 according to my problem. Okay, ma'am.
Yeah.
And actually, we show here D satisfies all the metric space property, but actually S with D does not satisfy the triangular property of the metric space property. We show this actually S does not follow the metric space triangular property,
Okay.
and we contradict the result. Okay, ma'am.
You mean the triangle inequality?
Yes, ma'am. Yes, triangular inequality.
Okay. So what exactly are you trying to prove? I mean, are you trying to prove that this thing is a metric or
Yes, ma'am.
something like
Actually,
that?
D S with D is a metric space. Okay, ma'am. Actually, we see here the D S with D is a metric space. Okay, but D does not satisfies the metric space triangular inequality. Okay, ma'am.
Okay, but sorry, I'm still not getting it. So S is the spanning tree. S is the set of all spanning trees. And
Yes.
what is the other thing? The D?
Sorry, ma'am.
So you were talking about some D, right? Sorry,
Yes.
I mean to say for some a metric space, you need to have some distance thing. So what is that distance? Distance between two edges? Sorry, distance between two vertices. I mean to say if you take two vertices, then number of edges between them or something like that. The shortest
distance I
number
think he has defined as number, like given the spanning trees, the different distance is number of edges that are unique in both of them. So the number of different edges in those trees that I think he has defined as distance.
number
from what I could
of
get.
edges that are present in the spanning trees.
Number of edges that are, so for two trees Ti and Tj, number of different edges in Ti and Tj. So
Oh,
basically what
okay.
we
So
need.
that is the distance. Okay. So if that is the distance, then you were saying that SD is a metric.
Yes, ma'am. S with D is a metric.
But you pointed out that it is not a metric. I mean to say, you just told that,
D
yeah.
greater
So
than equal to 0 and D is a symmetric.
okay. So, but the triangle inequality does not hold.
Yes, ma'am. Actually, suppose if the graph is disconnected, we assume that the graph is disconnected, and suppose we the vertex Vi, Vj, Vk, okay. And since the graph is disconnected, we cannot a path from the vertex Vi to Vk, suppose, and suppose there is a path Vi to Vj, okay. And since Vi to Vj there is a path, so the Vi and Vj neighbor to each other, and the corresponding the spanning tree is Ti Tj, and D of Ti Tj equal to 1, and D of Ti Tk is 0, and D of Tj Tk equal to 0. Okay, ma'am. And D of Ti Tj we can write d of ti tj equal to less than equal to d of ti tk plus tj tk, and
Hmm.
left hand side is 1 and right hand side is
Hmm.
0 plus 0. So
Hmm.
1 less than equal to 0.
No, that is okay. That is okay. But from here, how can you say that this whole thing is contradicting this problem? I mean to say that G prime is not connected.
Yes, if we consider the graph is disconnected, we consider first, then the actually does not satisfy the all the matrix space property on the set S. But the function defined here, d of d on the set S, the distance between two spinning tree ti tj is the number of edges of the of G present in the other present in one tree but not in the other tree. Okay.
Okay. No, that is okay. That is okay. So are you trying to prove that G prime is not connected?
No, ma'am. Actually, G
You are
prime is connected,
contradicting.
but
You
we
are
first
proving this
assume
by
that G.
contradiction, right?
Yes.
Okay, so you are proving this by contradiction. Okay, so I will try to have a look at your solution later. Okay.
Okay, ma'am. Okay.
Okay. So this is our problem, and I will just
Hello, ma'am.
hello.
Ma'am, Dhananjay assumed that the graph is disconnected, but if G is disconnected, how can we have a spanning tree?
Oh, did you assume that
Yes,
the
yes,
graph is
ma'am. He
disconnected?
assumed G is, yes, ma'am.
Oh, no. You cannot have a spanning tree in that case.
The graph is explicitly given in the question to be a simple connected graph, I think.
Yeah,
Like, it is
it is given
explicitly
as a
given.
simple
Yes,
connected
yes.
graph. Otherwise, you cannot have a spanning tree.
No, ma'am. Actually, I consider the G dash. Okay, ma'am. We assume the G dash is disconnected. Actually, we have to
Oh,
prove
yeah.
the
So you have
whether
assumed G to be
G dash
connected.
is
G
yes,
is
ma'am.
connected, right? Okay,
We
yeah.
have to prove the G dash is connected or disconnected. Okay.
Okay. Okay, so so you have assumed G prime to be disconnected, and then you have, I mean, you have arrived at a contradiction or something like that, right? Using the metric method.
Yes, ma'am. Yes.
Okay. So I will have a look at your solution, then maybe I'll let you know. So the idea is, so if we consider two edges in G prime, let's say G prime is the graph that the graph with all the spanning trees. V prime is the set of vertices, and E prime with the set of edges. We know that V prime is equal to S. So let's take two elements from V prime. Say, let's say T and T1 and T2. These two are two spanning trees. So if we have say we have d number of edges different which are present in T1, d edges which are present in T1 but not in T2. Now we know that number of edges in a spanning tree is always this thing, right? Sorry.
Yes, ma'am.
Therefore, we also have D edges which are present in T2 but not in T1. Now, we know that if we remove an edge from a spanning tree, then the graph will be disconnected. I mean, the tree will be disconnected, right? So let us consider some edge E in T1, which is not present in T2. Remove this edge from T1. Check in T2, find some edge in T2 by which we can make this graph connected. Also, I mean, if you cannot find any such edge, maybe let's say you have, I mean to say, let's say you have some other edge. I mean, I mean, we need to find some path, right? We need to find a path from T1 to T2. So after doing this, that is after doing this thing, that removing some edge from T1 and then adding that edge in, I mean, removing an edge which is present in T1 but not in T2, and then adding some edge from T2 to restore the connectivity of the tree. In that case, we will obtain some other spanning tree, T3, say. We will obtain this after performing this operation, that is removing E from T1, then adding an edge E prime from T2 so that we obtain another spanning tree T3. We will keep on doing this. And ultimately we will obtain T2 from T1. So this can also be shown using induction. I mean, basic step is, let's say, if we take T1 to be the, what to say, let's say Tn be the spanning tree, I mean, be a spanning tree. So let us consider T1 to be the, I mean, I mean, n equal to 1 to be the basic step. So in that case, we have T1 and let's say we have E in T1 and E is not in Tn. So we also know that if we add this age, so we have a tree here. This tree. And if we add an age, in that case, we will obtain a cycle. That cycle will be unique, right? So from that new cycle, let's say we are adding this age. So from this new cycle, from this thing, we will choose an age and we will remove it. This thing is GN, say. So from this new cycle, TN, sorry. So we will just remove the age and denote this graph by Gn minus 1. Keeping, sorry, again. So this is Tn minus 1. In this way, continuing in this way, we can obtain T2. So as we can see, all the graphs, I mean just all the spanning trees that are obtained are neighbors of each other. So we have a path from T1 to T2 in G prime. And as the number of edges that are different in T1 is equal to the number of edges that are different in T2 from T1. So there won't be any clash. I mean to say, it won't be the case that we will be removing edges and we will obtain some graph which is not connected or something like that. So this procedure will, this will help. I think, this will help in obtaining, in proving the fact that our graph G prime is connected. So is this clear?
Yes, ma'am, yes.
Okay. So now let me solve problem number 1. Was this done in class? I mean to say in any of the tutorials? Hello?
So inductions and like ON, inductions with ON has been generally covered in the last tutorial. So mostly yes.
Okay, so induction with what did you say? Sorry, I actually couldn't
Big O
hear.
notation, induction on Big O with Big O notation has been covered in the last tutorial.
Induction on big notation in the sense substitution method, the method of substitution.
No. So we did not have any familiarity with the big O notations and using them in inductions like assuming Kn and these processes
Hmm.
and induction in general. Both of them have been discussed in the last tutorial.
I see. So you don't know. So do you people know the method of substitution?
Method of substitution means
Means you will substitute and you will assume this to be so okay. So maybe
okay, like x squared, like these forms, and then solve for the roots and propose the
yeah.
result,
So
right?
let's say forget about problem number 1. It's just let's take a simpler example. Okay. So let's say we have some Tn is equal to T 2 into T n by 2 plus n. Now let us claim that our Tn is less than equal to Cn log n for some constant C greater than 0, and this C will be determined later. So the method of this is called method of substitution. So this is our statement. We need to prove this using induction. So have you people done this before?
No, ma'am.
No. All right, then let me show. So this is our claim. Now basic step is for n equal to 2, T2 is equal to 2 into T1 plus 2. So let's assume T1 to be equal to 1, say. So in that case, we will have this. And this equals 2 plus 2, that is 4. And that is less than equal to 2C log 2, which is equal to 2C. So this is true for n equal to 2. Now, let's look at the induction step. So let us assume that our claim, the claim that we have here, let our claim be true for all k less than n. Then Tn equals 2T n by 2 plus n. This is less than equal to 2 into Cn by 2 log n by 2 plus n. And this follows, this holds by induction. Now this is less than equal to, this is equal to, sorry, Cn log n by 2 plus n. That is again equal to Cn log n minus Cn plus n, which is clearly less than equal to Cn log n. I mean to say, we need to take C to be greater than 1 in that case. We already stated here that, I mean, C will be determined later. So clearly Tn is less than or equal to Cn log n, where C is greater than 1, and this follows by induction, and hence we have Tn to be equal to order of n log n. So this method is known as method of substitution. Is this clear?
Yes, ma'am.
Okay. I think all the other problems have already been solved in the class, in the other tutorials, right? Hello?
Ma'am, you
Yes,
are
yes,
audible, but I don't know that if it has been.
Sorry?
I don't know, ma'am, if that has been done. Somebody else should speak up.
Okay. So as okay, so I was being told that all the
Yes,
others.
ma'am,
Yes,
I think all of them are
all the-
done.
Okay. So do you have any other doubts?
No, ma'am.
Okay, so then I will end the tutorial here today.
Okay, ma'am.
Okay. So bye everyone.
Thank you, ma'am.
Okay.
Thank you, ma'am.